Hey,
Hello.
how are you?
I'm good. How are you?
Good, thank you. All right, what's new?
Not much. Um, I've I sort of want to focus on chem phys in this section or genetics, either one.
Okay.
But I don't have a specific passage. Do you have any material that we could go over or like a topic that you would recommend that's very high yield?
Yeah. You don't have anything from like that practice test that you took?
Um, Not really. Like I feel like
Mm-hmm.
I I reviewed it with another friend and together, so it was really cool, good to like do it with someone else. And I think we reviewed that section very well. I have some things from like biochem, but I really wanted to focus more on Tempest. Mhm.
Got it. Okay. All right, so what are some topics that you would want to go over?
Um,
I think I wrote down for you, oh, okay. Let's see. Okay, maybe I can look through some of my whiteboards.
Maybe.
Um,
I could also just like generate like a passage from UWorld and we can go over it. If that work. Yeah.
okay.
I don't know. So let me know if I should.
Mhm. Yeah, maybe you can do some stuff from physics
From
or
physics.
Gen Chem or whatever.
Um, yeah. So let me know what you prefer, like if we should do like if I should do something or if you have any material.
Yeah, you can use UWorld and we can choose. So like, okay, let's see. Yeah, so why don't you share your screen and we can kind of decide. All right, so um okay, yeah, so from the topics under Gen Chem and the topics under physics, which topic would you feel like you feel the least comfortable with?
Honestly, probably the first, surprisingly, or in this one, these two.
Okay, we could do that.
So I guess I can just generate like probably 9 questions.
Um, let's see. Nine. What um yeah, we could do that.
Okay. So let me just take it off of people tutored.
Mm-hmm.
So during beta decay,
Mm-hmm.
um, a radioactive atomic nucleus emits either an electron or a positron. If a cobalt 59 atom is formed from the beta minus decay of a radionuclide, what must the original nucleus have been? So they're telling me that so this is probably 59 is like the mass number, so it's the proton plus
Uh-huh.
uh electrons. Is that correct?
So, all right, let's talk a little bit about this stuff. So basically, in an atom,
Neutrons.
yeah. So
Yeah.
yeah, in an atom, the nucleus will consist of protons and sometimes usually neutrons as well. And let's say there's an electron around it. So okay, so let's talk about, okay, the proton, the neutron, and the electron. So like, okay, let's talk first about mass, and then Q would be charge. So the proton will have a mass of, we just call it like 1, like atomic mass unit, AMU. And the charge will be +1. For the neutron, you're not going to have a charge, so a charge of 0, but a neutron will have the same mass as a proton, so the mass will be 1. Now, the electron will have a mass of 0, but its charge will be -1.
Yeah.
So, oh yeah, like that question that we had last time with the negligible mass, I was going to say, like, the mass of an electron is really 1/1800th of the mass of a proton.
I see. Yeah.
But we say it's negligible, so we say it's 0.
Yeah.
So yeah, so that's that. Now, so that's how an atom works. Now, there's different types of radioactive decay. Um, what are what would you yeah, what
Yeah.
types are you, I guess, aware?
Yeah. I remember it's been a while, so I don't have it that fresh. But I know like that there's something like from like there's alpha decay, beta decay, there's like gamma radiation or decay. And I know that it's like there's different cases. So like a proton, um like if or you can either like increase the mass number or decrease the mass number, or it might stay the same. And it could be like neutron becomes a proton or something like that by absorbing something else.
Mm-hmm.
Or a proton dissipates. I don't know. This is just what I'm remembering. Um,
All right, let's
yeah.
talk a little bit about these radioactive things, right?
Yeah.
So the alpha particle, what can you tell me about the alpha particle in terms of charge and mass?
Mm,
So, all right, so I'll tell you. So,
yeah.
the alpha particle, you will sometimes hear it described as a helium nucleus.
Okay, I see.
Yeah.
So it's positively charged and it
Yeah.
has a charge of 2.
Yep. So yeah, so it'll have a charge of +2, and what do you think its mass would be?
Um,
Mm-hmm.
the 4? Yeah.
So, so okay. So sometimes people think that it's just the same thing as helium, but what makes it a helium nucleus rather than a helium like atom?
As if it's a nucleus and it doesn't have the electron cloud.
Correct. Which means it would be positive, right?
Yes.
So nuclei will always be positive. So that's why even like when you think of like a nucleophile will like to bond to something that's positive or partial positive. So okay. So That's an alpha particle. It's equivalent to a helium nucleus. Okay. Now I wrote beta twice. Why would I do that?
I know that there's positive and negative.
Yes.
Uh, yeah.
What do you think the mass would be?
Um, um, maybe two. I don't know.
So the only thing that will have only radioactive I guess particle that will have mass will be the alpha.
What would be the what? Sorry, can you repeat that?
Yep. My mic messed up. Can you like hear me? Test. My mic's all the way over there.
Yeah, I can hear you. Yeah.
Okay. So yeah, the alpha particle will be the only radioactive like decay particle that will have mass.
Oh,
So
I see.
yeah. So this would have a massive zero, this will have a massive zero, this will have a massive zero. Electron capture I'll go into as well, but electron, so massive zero. Okay, good. And then we could have a beta minus, right? So let's say -1, or a beta plus, which will be +1.
Yeah.
Now, the beta minus is basically just an electron. Okay. Uh,
Yeah.
oh, and then I should also say -1 for
I think
electron.
I'm remembering like beta minus, the way I remembered a long time ago was like it's actually increasing the proton number. So it must be that probably a
Oh,
neutron.
I guess you're thinking of like when you do the entire radioactive like equation.
Yeah.
Got it. Yeah, I'll go into that in a sec. Um, but yes, so the beta minus is equivalent to an electron. So it'll have a massive zero and a charge of -1. The beta plus is something called a positron, which is essentially imagine an electron that's just positively charged.
Okay.
So like an electron, it'll have a massive zero, but unlike an electron, it'll have a charge of +1.
Okay.
Okay, so this is a positron. Okay, all right. Now, what I drew here, I mean, this is supposed to be like this is my way of just drawing gamma, but gamma will have a mass of zero and also a charge of zero because gamma is a type of light,
Yeah.
and light doesn't really have a charge or anything like that, right?
Yeah.
Good. And now the last thing I wrote was electron capture. So that falls in the category of radioactive decay, but it's technically not a decay because what it means is that an atom will capture its own electrons, turning a proton into a neutron. So what I mean is, so okay, let's think about, have you ever heard of like a neutron star?
I've heard of it. Don't really know how it works.
Okay, so like well, what about like our sun? Like what happens in our sun? Um, in terms of subatomic particles and stuff?
Um, no, it's
Okay, okay. So, I mean, it's not on the MCAT or anything, but okay, so like us so our sun, which is a star, um has, gases which are expanding outwards, but the mass of the sun is so large that the gravity is also there and it's compressing things inward. Um, and the gravity is stronger. So the sun, the gravity is so strong there that so so it has a lot of hydrogen atoms. So let's say hydrogen, you know, charge of 1, mass of 1, it can take two hydrogen molecules or atoms and through the tremendous gravitational force, push them together to cause them to fuse. Now, generally speaking, atoms don't fuse, right? Because like this looks like this. It's a proton and an electron, right? And if I had another one, it'll be this thing also, right? So if I put both of these together, right, the electrons will be repelling each other, so I can't put them together, right?
Yeah.
So that's, if you think about it, right, we're both experiencing gravity, right? But why aren't we being pulled down to the center of the Earth? And so the reason is that the electrons of the atoms of our bodies repel the electrons of the atoms of like the chair that you're on, which repels the electrons of the ground, all of that stuff. So that's why we're not, even though gravity is something we're experiencing, and even though most of the atom is empty space, the reason that we're not, just going straight down or going through things is because electrons, repel one another. Like charges repel, unlike charges attract. So what happens with the sun is that the gravitational force is so strong that it is stronger than the electrostatic force that repels them, and therefore it fuses them together to produce helium. I know the 4 isn't making, sense exactly right away, but the thing is that one of these hydrogens will be something called tritium, which is just hydrogen with 2 neutrons.
Okay.
And yeah, and I actually have some like that I can show you. For instance, like, let's see. So this, and I'm gonna just try to block the light around it.
Yeah, I see that.
See that it's like
Glowing.
oh yeah. So tritium does that. So I have like my cat's like necklace is like tritium and it lights up and stuff. But anyway, so okay, that's just showing you. So this is called nuclear fusion. Okay. Now, if we can imagine, so the sun has a lot of gravity because it has a lot of mass, right? And that's just how it works, right? If something has mass, it must experience some type of gravity. Um, so if you can imagine our sun, right? Let's take its mass, let's make it 3 times more heavy. And let's take its radius, how large it is, and let's make it so it's as large as like the island of Manhattan. So if you have, yeah, what's up?
So you're making it a lot smaller?
A
Like
lot
isn't
smaller.
yeah.
So, but with a tremendously high amount of mass, like 3 times as much mass, but smaller, right? Um, so it's a lot more dense. Okay. And what happens there is because there's a lot more, because gravity, right, is big G, whatever, M1, M2 over R squared, right? So if you increase the mass to make it 3 times the mass, the gravitational force increases by a factor of 3, right? And if you make it smaller, that radius value gets smaller, right? Which means the gravitational force goes up even more, right?
Yeah.
So imagine, so this type of fusion, right? However, let's imagine it just for one atom. Okay. So what happens is instead of fusing 2 different atoms together, which is hard enough, um, it will fuse one atom together. So what happens is this proton and this electron fuse, okay? So this will be like, okay, like one proton plus an electron. So I should say, whoops. So like a proton with, charge of +1, a mass, yeah, mass of 1. Sorry, that negative should be not there. Oh, so okay, so 1 + 1 for the proton plus the electron, so that's going to be 0 mass, -1. What do you think this will turn into? Well, we could start off with the mass. What do you think the mass will be?
Well, I think is it a neutron?
Yeah.
Yeah.
Because
Yeah,
the mass will be 1 and the charge will be 0. And that's how you get a neutron. And that's why it's called a neutron star.
I see.
And a neutron is the hardest substance in like the universe. You know, I'll show you like a little like image a little later. But if you can imagine taking a single atom and compressing it so much, that is electron capture. So an electron capture is when an atom's nucleus captures its own electrons, turning protons into and electrons into neutrons. Okay.
I see. Yes.
Yep. So, okay, so that's electron capture, and as you can see, it's on the left side of the arrow. So it's, it comes up as a type of radioactive decay, but it's technically, gaining it. Okay, so that's an example of electron capture. For all of these other things, though, you want, or I should say that for all these other things, so like if the mass changes, it's going to involve some type of alpha particle. Oh, and then, yeah, so for the beta particles, though, it would be like, so beta decay would be like the reverse of electron capture. And if electron capture is taking a proton and an electron and turning it into a neutron, beta decay would be what? What do you think?
It's the neutron becoming a proton and removing the electron, like leave
Yep. So now a neutron will decay into a proton and an electron, and that electron is that beta minus particle.
and you just call it an electron.
You could call it an electron. You can call it a beta minus particle. You can see here they're saying electron in parentheses beta minus decay.
Okay.
And okay, now for the positron, right? You want it to emit something that would be, so like I'll draw the arrow first, and then I'll draw the positron. So that's 0, oops, yeah, 0 mass +1 charge. So this would be like a neutron. Oh, sorry, this would be like a proton turning into a neutron and a positron. So this would be like yeah, a proton with a mass of 1, a charge of 1, decaying into a neutron with a mass of 1, a charge of 0, plus the positron. And then yeah, the gamma thing is when you don't have a change in mass and you don't have a change in charge. So okay, so these are the different types of radioactive decay. And when we ask ourselves what type of decay something undergoes, we want to consider the fact that most atoms will want to have a 1-1 ratio of neutrons and protons. Okay? So if I were to, let's say graph that, so let's say this is the graph, and this is the number of protons, this is the number of neutrons. Generally speaking, like this line that I drew is like when they're equal.
Yeah.
So if they're not equal, then we would know what type of decay something undergoes. So for instance, let's say I had something here.
Yeah. It
So
looks like you've gained a proton
so
and
so an,
drained a neutron.
yeah, so an atom here would have a larger amount of protons than neutrons, right?
Yes.
Now, we would call this Neutron-Poor. Okay.
Sorry, we would call this a neutron,
Oh,
or
sorry. Here, let me move my mic closer. You hear me?
yeah.
Yeah, okay. So like if something was here, it would have equal amounts of neutrons and protons, right? But something here would have a larger amount of protons than neutrons. So we call this neutron-poor.
I see.
So the type of radioactive decay it will undergo will be something that will bring it back to that line, aka something that will make neutrons. So what type of decay might this turn into?
Um, Beta positive.
Mm-hmm. Yeah, right. A proton, we have an extra amount of protons and not enough neutrons, so we can take a proton and turn it into a neutron with the beta plus decay or positron emission. And then, vice versa, you would have, I'll make it like pink, let's say something here. Now, this would be having a higher amount of neutrons than protons, right?
Yes.
So this would be neutron-rich. And it will undergo a type of decay to have, an equal amount of the two. So what type of decay do you think it would undergo?
Beta minus.
Yep. Because you're going to have, if you have too many neutrons and not enough protons, you can take a neutron and turn it into a proton. Good, good, good. So, okay, so now if I gave you like, let's say, um, if I asked you about, let's say, C14.
C14.
Yeah, so carbon 14, that number will be the mass. Yep.
Oh, I see. So carbon normally has, is it 6?
Mm-hmm.
6 protons?
Mm-hmm.
Check that radioactive. Yep.
Mm-hmm.
And so 14, that means that it has more neutrons than protons. It has 2 extra
Mm-hmm.
neutrons. So it's neutron rich,
Yep.
and it wants to become, it wants to lose these neutrons. So these neutrons are going to become protons.
Uh-huh. So
It
so
emits,
uh-huh.
yeah,
Go on, go on.
it's and emits an electron or a beta decay particle.
Yep.
And
Because it
yeah,
would be
yeah,
this situation, right?
yeah.
So okay, so now we want, an arrow, and we can draw like the because the thing is, when we draw like the actual like radioactive decay thing, we're not really gonna draw like the proton or the neutron or anything like that. We're just gonna draw the new like atom, I guess, and the decay particle, and it can only be, one of these over here. So we know that it'll be beta minus decay, so we know that this will be like that, right?
Yes.
Now, what you were saying earlier about, everything on the left has to equal everything on the right, like the masses have to equal everything, and the proton number or the charge and stuff. So, okay. So we drew our beta minus particle. Um, Now we know that that's accounted for over here, right? But we know that we're also adding a proton, right? And if you change the number of protons in something, it changes that element's identity, right?
Yes.
So what do you think will happen with this? Like, what would go here?
Um,
You could start with
so,
the numbers.
um, yeah. So this is beta decay. So the mass number should not change. So the 14 should stay the same. And the uh proton number, the atomic number, should go up by 2.
So, you know, let's say that it did. This would then be 8 minus 1 or 7 on the right. But we want it to be like 6 on the right. Right?
Sorry, I just didn't understand that. Could you explain it again?
Oh, sure. So let's say it was 8, right? Then everything on the right, if we added, like the 14 plus 0 will be 14, and that matches with the left. But the 8 plus -1 would give you a 7 on the right.
I see. I see.
So
Yeah.
what would this number be to give you a 6?
But
Hmm.
I guess it would be 7, but I thought there were 2
Um,
necessarily, like the mismatch. And I thought we wanted it to be equal, did we
so
not?
now it will be equal, right? Because if you have 7 protons and the mass is 14,
Right.
right?
Right. I was thinking of the carbon other example.
Mhm.
Uh
Now, what would this turn it like? Is this carbon anymore?
no.
What is it? Yep.
It's nitrogen.
Yep. And this is carbon dating, like what they do in carbon dating.
I
Like,
see.
because when like an organism dies, it stops taking in carbon from the environment. So you can measure the amount of carbon in that organism or fossil or whatever, and you can measure the amount of nitrogen, and that'll let you know, how much of it has decayed. And using a half-life and stuff, you can figure out how old something is. But yeah, mostly what you see here is just that because I know that like at first you were thinking of you know the change is like 2, but generally speaking, like you'll even if you see that the mass number is different from the atomic number by more than 1, you'll often see that like that whenever you write this, like it'll be like for one kind of decay reaction at a time.
I see. Yep.
Yeah, but mostly you want to just see that. Okay, so carbon has 6 protons, and if this type of carbon has 14 as a mass, it's neutron rich. If it's neutron rich, we want to take a neutron and turn it into something that we want more of, which is a proton, and that can help you know what type of decay something will undergo. So let's say, how about beryllium 7?
Is it, I think the it's 4 for beryllium, right? The proton number. Um so that means it has one less neutron than it should, right?
Mm-hmm.
So we are neutron poor,
Good.
and we're going to want to uh we're neutron poor, we're going to want that uh beta positive decay.
So we could do something. Okay, so if we did that, right? Um yeah, we would get, okay, yeah, we could do that. We could do that. I think we can do that. I was thinking of um electron capture.
Oh, electron capture. Okay.
Yeah. Um but let's see if the positron emission can happen. So if that were to happen,
Can I think about it a couple more seconds?
yeah, of course, of course.
Yeah. Um, yes. So beta positive would actually decrease my protons. And so instead of having 4 protons, then I would end up with 3 protons, right? Instead of 4 at the end. Um, uh, which I guess is possible, right? But I don't know if it's the ideal, right? Instead of, as you were saying and implying, like increasing, I guess, the amount of neutrons as well. Mhm.
Yeah, yeah, yeah. I think I
If
think I
Mhm.
think both would work here. So either one would work. So okay, let's try the positron part then, or the positron emission. So we would have, something like this, and we would have, you know, this positron here, and then this would have to be 7. And what would the atomic number have to be for this new thing?
um 3.
3. So it can undergo that, and it will turn into, I think,
Lithium.
yep,
Mhm.
good. And let's see if it can also undergo electron capture. So 0 minus 1 electron, and then it turns into, yeah, the same thing. So yeah, either one can work here. Yeah. And okay, good, good, good. So I think the last thing that I just want to tell you is that um once you get to atoms that have an atomic number larger than 83, which is like uranium, like once you get past that point, because if you think about it, right? A nucleus consists of protons and neutrons, right? But don't like charges repel? They do. So, um, so in physics, I want to simplify everything by telling you that there's only 4 forces in the universe. Okay. Like normal force is a consequence of like something else, and buoyant force is a consequence of something else, etc. But the 4 like at a distance forces, so there's gravity, there's electrostatic, which includes, magnetic. Then we have something called a strong force and a weak force. Now, for the MCAT, you really just need to know these two. But um, but I'll tell you what the others do. So the weak force is just the thing that's responsible for radioactive decay. And the strong force is super strong, which is why it's called that. But it can only operate within extremely short distances, like the short distances between protons in a nucleus.
Mhm.
So, so let's say that we just have, like these two protons here, and this distance between them, let's say that this is the maximum distance for, because these two protons are experiencing both a strong force and an electrostatic force. The strong force keeps them together. Electrostatic, repels, pushes them apart. So let's say this distance is the maximum distance at which the strong force is larger than the electrostatic force, right? And let's say we take a neutron, right? And we like kind of shoot it in between there. Let me actually draw these a little closer. Like that. So let's shoot the neutron there, okay? When you do that, right, if you have like, I'm trying to see if I have like two circular things or whatever. Okay, two kind of protons here, right? I know they're
Yeah.
not exactly equal and stuff, but if I shoot something like in between here, it will force to get through, it will force it to move away from each other, right? And if this already is the max distance for the strong force to be larger than the electrostatic force, when you shoot that neutron in, it'll be pushed beyond that distance, and then the electrostatic force will take over and they'll repel. And this is called nuclear fission, the splitting of an atom. So that's, when they made the atom bomb, they basically took uranium, shot it with neutrons to cause the electrostatic force to overcome the strong force, which causes the atom to split, and it shoots these, neutrons all over, chain reaction, etc. You get the atom bomb. Later on, we made something called a hydrogen bomb, which takes advantage of nuclear fusion, like the sun, and that's a lot more powerful. But yeah, basically, that's all the stuff for atomic stuff, like the atom and all that stuff. So yeah, what do you think? Oh, and then last thing I should just say is that this is like with these large things, that's typically when you'll see some type of alpha decay.
Okay.
Yeah.
Um, Alpha Decay. So the first one. I guess could you explain a bit more of like what is happening in an alpha decay? Like I get like the 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 charge, not the charge difference, like the helium is emitted, so like what it's changing by and how to identify it a bit. But like what is happening there?
Yeah. So okay. So basically, you know, I guess we can ask ourselves, why release an alpha part? Why not just release two protons and two neutrons, right? That should be the same, right? But there's something called a mass defect, which means that um okay, so for an alpha particle, um if you sum up the individual masses of the two protons and the two neutrons, the mass of the alpha particle is less. So I'll write that. So like the mass of an alpha particle is less than the masses of like the two protons and the four, or wait, what am I talking about? Yeah, and the two neutrons. Um so yeah, so what I'm trying to write here is that the mass of the, like, okay, a helium or whatever, yeah, a helium or an alpha particle theoretically should have the same mass as the sum of two protons and the sum of two neutrons, but it's actually going to have a lower mass. And, it sounds like it's a violation of the conservation of, mass, but uh, the alpha particle, so when you have a mass defect, that means that, so, there's E equals MC squared, um, which essentially tells you that mass and energy can be interconverted. So the alpha particle will have a lower mass, which sounds like it's a violation of conservation of mass, but there's conservation of energy. So really what's happening is that smaller mass means that it's already converted some of the mass into energy, which is why the alpha particle that decays has a kinetic energy, which has it moving. Because if it was not that, and if it just released, like whatever, 2 protons and 2 neutrons, that would be an equal amount of mass, and there's no extra mass to give to energy, so the thing will just stay there. It won't move. So yeah, so that's why the alpha particle is a thing. And all of these decay things, they actually have kinetic energy. They move, they like shoot out. So that's why yeah, this is called the mass defect.
And I guess I'm also remembering or misremembering, but you can correct me.
Mhm.
Something about like the distance or like what it can travel through. Like I remember an
Oh yeah,
image.
yeah. That was gonna be the image that I was gonna send you. So yeah, let me show you. Um um
Should I stop share?
oh no. I'll just send you like um here, one sec. So just click this link and share it and you'll see. So yeah. So actually why don't you just take a quick screenshot of everything so you can get it, and then I can talk about this, but
Yep.
yep.
Yeah, sounds good.
Yeah, so here we go. So here we have the different types of penetration power. So the alpha, it's calling it rays, but whatever. Yeah, so the alpha particle can be stopped by something like paper. The beta particle can penetrate paper, but it can be stopped by, a low density metal like aluminum. Um, Aluminum is low density. Uh, if you want to like think of a real life example, think of like what planes are made out of. They're mostly made out of aluminum because they're have a low density, and if you want something to fly, yeah, that can help. Gamma rays, which are super dangerous, can penetrate all of that, but can be stopped by lead, right? Um, but yes, the neutron, uh, you don't have to know about like neutron decay or any of that stuff for the test, but just to kind of bring home the idea of what I said, like the neutron's the hardest substance in the universe. Um, that's why it can penetrate lead, uh, but it can be stopped eventually by concrete. So yeah, that kind of shows you like the different types of penetration. That was kind of like what you're asking about, right?
Yes.
Yeah. There's also a kind of uh counterintuitive kind of thing that they might ask you. Like for instance, if they ask you like, okay, what's more dangerous for us like to be exposed to? Like for instance, like out of all of these, like you would think that it would be the gamma ray because that will have the highest energy and it has such a small wavelength that it would mess up things like on the subatomic level. But the thing is, the gamma ray travels at the speed of light. So if it penetrates your body, it does that for such a tiny, tiny period of time, right? Compared to the alpha particle, which can penetrate like your skin a little bit, but it isn't gonna go through it. So it's gonna get stuck in the body. So so sometimes you might be asked like what type of decay is the most dangerous? Um
Could it be also because it has mass? Uh,
so the mass part, I mean, that can that will probably play a role in why it isn't so easily, why it doesn't penetrate so easily. But it has a greater stopping power because it can stop and stay in your tissue, and you don't want that. That's going to be bad.
Okay.
Yeah.
Yeah.
So, so okay, that's all this stuff. So yeah, what are your thoughts?
It's I guess I could try to see if I really understood it, summarize it in my own words. So we sort of went over the radioactive decay, and there's alpha decay, beta decay, which can be positive or negative, and then gamma, which is like energy, like gamma radiation, I think. And there's also electron capture. So for alpha decay, you see that a helium, like, I guess I'll go over what's emitted. Like you have a helium nucleus. The for the beta, which is massive for proton number two, for
Mhm.
the beta positive, sorry, for the beta minus decay, we would have the electron, and for the beta positive, we would have a positron emitted.
Mhm.
For the gamma, it's just energy, gamma waves, gamma. And for the electron capture, you're releasing a neutron. Neutron?
Mhm.
Mhm.
Yeah, yeah.
Yeah.
So, good. Okay. So, yeah, good job. So, let's do that question then.
Yeah. That was useful
Yeah.
to review. Okay, so during beta decay, a radioactive atomic nucleus emits either an electron or a positron. Okay, that's two different types. If a cobalt-59 atom is formed from the beta minus decay of a radionuclide, what must the original nucleus have been? So cobalt-59, I guess I can look up the cobalt.
Mhm.
Cobalt 27. So cobalt has a atomic number of 27. And here we have that it has 59, 59 in total. And so I can do the subtraction. So we sort of have 32. And so if it has 27, okay, 59 minus, if it has 15, if it's 27, it should have, like, if it were neutral, then we would think cobalt would have also 27 neutrons, right? So we would think that it would have a mass number of 54.
Well, let's try like this, right? Because, um, so like if they asked you like what type of decay this undergoes, then you can do what I showed you with, is this neutron rich? Is this neutron poor?
I
Right?
see. Yeah.
But they're already telling us that this is a beta minus decay.
Yeah.
So what I would set up is like, you know, the thing
Or beta
zero and
one.
stuff.
Mhm.
So like, okay, cobalt 59. So they tell us that the mass is 59. So I'm going to put that as the mass. We looked in our periodic table to see that the atomic number is 27. So I put that. Now what should I do?
Um, oh yeah, you're right. They are telling us it's beta minus.
Mhm.
So in beta minus decay, uh, we ended up with emitting an electron,
Uh-huh.
and my proton number went up, right?
Uh-huh. So yeah, what I would do is just set it up like this, right? So I would draw that cobalt 59 that's produced, the beta minus, so this is -1 and 0, right? And then an arrow like that, and we just need to see what's this original thing.
So I guess it would be something with atomic number 26, right?
Yep. What are the
So iron, Fe?
Well, yeah, okay. Let me see something though. Yeah, 26, 59, and I think that should be it.
I think it should be it too. Let's see.
Let me check something. So
Yeah.
if we have, let's see. Okay. Oh, yeah, yeah. You already, all right.
Sorry, I didn't realize you
Got it.
did that. Just
So yeah, okay. That makes
yeah.
sense, right?
Yes.
Good. Okay. And yeah, let's do like
Yeah.
maybe one more.
Do we have time? We actually don't have much time.
But we covered a lot.
Yeah. Um,
Oh, so this is going to be like talking about half-life of some sort.
yes.
Let's see if we can see another like decay type question. Oh no, we're gonna go into like passages and stuff. All right, let's see if we can do this then. Here, I'll clear this. Or if
Sample
we have, yeah. Huh?
42 table time and the activity. What must the initial activity of the sample happen at 0 hours? So, oh, I see. So we're giving time and activity, and I sort of have to find the what the initial one was. And it's decaying by a constant amount, right? It's funny because I know the formula for like finding the half-life is 1/2 to the n. And then I know that to find the remaining things would be 1 minus 1/2 to the n. But I don't think that helps me that much. Because I need to find n, right?
So you can kind of like, you know, subtract like see how the activity changes
Yeah.
for these, right? Like, because you know, this is like
It's linear, right? Is it? So could I,
Mhm.
the initial activity at 0 hours had to be, do I have to do a calculation or can I try to find a pattern?
So what I would do is, well, okay, so like kind of like what I would do is like I would subtract this from this, see what I get, and that's over
Mhm.
3 hours,
Yeah.
right? And then I can see if it's, it should be the same for this. But what we can also do, like we're gonna do that, but we can also eliminate some of these choices,
Yeah.
right? Because we see that it's
Yeah.
going down.
Yeah.
So what can we well,
Um, I guess, I don't know. My guess would be D, but just from like a pattern perspective, just by like the rate of how much it's changing, and like I'm being asked what would it be at a time if there were another line, another row
like
here.
400, right?
Yeah.
Roughly.
Yeah.
Oops. Kind of like 400, right?
Yeah.
So it would just be the 112 plus like 400. So yeah, you have good instinct. So I would say that should be it. I didn't do like the math
Me
specific.
neither. Yeah. Okay.
Awesome.
I guess this is what we do when we're on a time crunch.
Yeah. So yeah, so for this one, we just would have, just seen how, the activity goes down, like by how much, and the time goes down by 3 hours each time. So you would just then add that amount for 0 hours. All right.
Sounds good.
Awesome.
Well, thank you. I
Mhm.
definitely have to keep working on ChemFiz.
So
Uh,
I have in the PDFs, I have a a PDF called Radioactive Decay that you can take a look at.
Okay.
But yeah, for the other stuff, then yeah, you can practice that. And do you want to meet on Saturday? You take another test?
Yes.
Sunday?
Sunday.
Um, Sunday at 3 p.m. Eastern,
Yep.
that works.
That works.
Awesome. Okay. So good luck on the test that you take on Saturday, and
Yes.
I will see you on Sunday, okay?
Thank you. Yes. Bye.
Thank you. Have a great week and stuff. All
Yep.
right.